Hello, in this video we're going to consider on Fourier series. Generally, Fourier series are known as tools that can be used to show alternating functions to the form of the sum of trigonometric functions such as sinus or cosine. You might ask, why do we get this summation of alternating functions? There should be a reason, and the origin of this rule turns to this point that all the arbitrary functions we are asked to represent are alternating functions. So the main function should be alternating too. Initially, let's have a look on orthogonal functions. We assume that both f of x and g of x are a piece of interval functions and it's currently defined from a to b. And if the integral of the multiplication of f of x to g of x from a to b is equal to 0, we will get this as a conclusion that these two functions are orthogonal. For instance, we approximate L as it is equal to the half of the period. And we get the high frequency functions that I wrote down here, cosine n pi over Lx and sinus n pi over Lx, that are interval from negative L to L, so they are orthogonal. Here we got some of those important integrals that later we might need them. For example, the integral of cosine n pi over Lx dx from negative L to L would be equal to 0. Also, we have the same rule for sinus x, so we reach to this point that the integral of sinus n pi over Lx dx multiplied to cosine n pi over Lx will be 0. Also, there are some special occasions in which the answer of the integral is dependent to m and n. I got an example. The integral of sinus n pi over Lx multiplied sinus m pi over Lx dx from negative L to L. If we get the m equal to n, the answer will be L, and if not, the answer will be 0. In addition, this formula is set for cosine. Now we're going to compute the Fourier series for periodic functions. That will be half of a sub 0, the constant part, plus sum from 1 to infinity of an cosine n pi over Lx plus bn sine n pi over Lx. The point is, the n pi over L part of these trigonal functions represents the effect of different frequencies on the behavior of the function. And we are ambitious to compute the a sub 0, an, and bn. I'm going to point out how to evaluate the a sub 0 coefficient, so I take the integral of both parts from negative L to L. Later I'll tell you why do I do that. I take the integral from both sides of the equation. This would be the result. We just have to take this integral with help of the integrals we computed before, and the integral of sinus n pi over Lx dx from negative L to L plus the integral of cosine n pi over Lx dx from negative L to L would be 0, so an and bn are equal to 0 too. A sub 0 coefficient just remained, and this is why I took the integral from negative L to L. I'm going to evaluate this integral. Here we have a sub 0, which is equal to 1 over L, the integral of f of x from negative L to L. So now what we're going to do is walk through how we compute an coefficient. I have to multiply the whole equation to the function generated from an. Eventually, I evaluate the integral from negative L to L. That generated function is cosine n pi over L. I will multiply it to this equation, then take the integral. I will get this as a result, and I will evaluate the integral. This integral becomes 0, the same as the last one. And the answer of this equation would be equal to L. To simplify, the integral of f of x cosine n pi over Lx dx from negative L to L is equal to an times L. So my an coefficients are going to be given 1 over L, the integral of f of x cosine n pi over Lx dx from negative L to L, and similarly I use the same method to evaluate bn. Okay, then Bn would be 1 over L the integral of f of x sinus n pi over Lx dx from negative L to L. So I would explicitly write this out that generally Fourier series of a periodic function with periodicity equal to 2 times L and the domain equal to x from negative L to L would be this, and the a sub 0, a n, and b n coefficients would be arise of these formulas. For instance, we can find an by approximating 1 over L times the integral of f of x from negative L to L multiplied with an coefficient, cosine n pi over Lx. And we can get a0 by plugging 0 into an, so we will have a0. There's kind of example here. We're asked to approximate Fourier series of a function equal to x, which x is between negative pi and pi with periodicity equal to 2 pi. And here we're going to project an, a0, and bn. It is obvious that x is an odd function, and we got x domain between negative pi and pi. What I will do is to take the integral of this function to get a0. And I know that the integral of an odd function with symmetric range would be 0. So a sub 0 would be equal to 0. And again, we got an as it is 0. Why? Because f of x is an odd function, and oppositely, cosine is an even function. And the multiplication of these two functions would be an odd function. And properly, the answer of this equation would become 0 too. The next part, we're going to compute Bn. I just have to plug pi in terms of L and plug x in terms of x. And we will get this equation as a result. Let me mention this point that f of x is an odd function, the same as sinus. So that will be the multiplication of two even functions. And the integral of an even function would be equal to 2 times of the integral applied on half of the interval. Well, you can evaluate the integral of sinus x dx by both integral by parts or the table. So I got the table method here. We have x and sinus x. I derive x for a couple of times, and I would integrate sinus x for a couple of times again. Then I multiply each line into positive and negative alternatively. And finally, we'll get this as a result. The integral of x sinus nx is equal to negative 1 over n sine nx plus the negative 1 n squared times sinus nx. By plugging the bounds into the formula, the final result would be 2 pi times negative pi over n cosine n pi plus 1 over n squared sinus n pi, and by plugging 0, we'll have 0. I'll minus these functions. Sinus n pi would be 0, and cosine n pi would be negative 1 to n. And the product of these functions would be negative 2 over n times negative 1 to n. This is what comes in terms of Bn. By plugging into Bn coefficient in the main formula, we can find Fourier series of the function in terms of x between negative pi to pi. To put all in a nutshell, it would be the summation of 2 over n times negative 1 to n plus 1 sinus nx from 1 to infinity. There's a considerable point I'm going to tell you. If the periodicity of the function is 2 times L, we will set new formulas to find a sub 0, an, and bn. There's a little difference between them and last formulas, and it is their bound. That has been changed into 0 and 2 times L from negative L and L. Another super important point would be this, that if the function is defined in the range from x sub 1 to x sub 2, we can turn the bounds into x sub 1 and x sub 2, and the periodicity of the function would be x sub 2 minus x sub 1. In fact, Fourier series is kind of series that may be convergent or divergent. To build your intuition for what we're doing here, I will expand on Dirichlet convergence theorem. Assume that f of x is continuous in negative L, L interval, Also, it is periodic outside of the interval with periodicity equal to 2 times L. So, in this case, I will get that the function will be convergence to f of x sub 0 in each arbitrary point in the integral. And on the discontinuous part of the function, or better to say, the beginning and the ending part of this interval, Fourier series would be convergence to the average point of the left and right side limit of the function. Here I'm going to focus on convergence and Fourier series behavior to make it stick out the mile. So let's put the example in test. I will plot both the function and the Fourier series of the function in MATLAB. For example, here we have n equal to 1, so I assume that I will plot both functions according to n equal to 1. I just want to plot the first sentence of this Fourier series, so here I have f of x equal to 2 sinus x. By plotting this on MATLAB, I will have this blue graph as it is the Fourier series graph, and the black one will be the graph of function plotted on 3 periodicity. Let's try something new. I'm going to increase n. For example, I assume n as it is equal to 3. So I have to write 3 parts of this function. Well, I'll get f of x equal to the first 3 sentences of the Fourier series. By plotting them, this blue graph represents. If I add up the sentences, for example, if I get the first 8 sentences, I will have another blue graph. There are some distinct graphs and there is difference in the convergence. How? As the number of sentences increases, the Fourier series in the known domain becomes more convergent to the function itself. Additionally, the Fourier series in the domain is convergent to the main function, and it is convergent to the average point of the left and right side limit in the discontinuous interval. This is the average point, equal to 0. As can be noted, the average point of this limit is algebraically equal to 0. I truly hope that you enjoyed this video and it was effective for you.